credit card transaction, right? Like for instance, I don't know, you withdrew money in different country from the one you're usually withdrawing for a large amount of money. So since this is unusual, then you should assign low probability to that, let's say that transaction, and then banks use this to say raise flags, right? Like say, okay, this transaction looks very unlikely, so meaning that the probability of observing such transaction is very small, and so people use this to raise flags, right? Like and say, okay, we should look into this transaction more carefully. As one example of the use. So in physics or in machine learning, people study these probabilities, right? Like over data sets of real life data or observations, right? But in statistical mechanics, we do something very similar, which is we want to assign a probability distribution to a physical, say a physical configuration, right? And so we know that in equilibrium, in statistical mechanics, this probability of observing some configuration is related to its energy under some energy function or Hamiltonian E. And so the Boltzmann distribution is given by this object here, right? Like it's E2 minus E, the energy of the configuration, divided by the Boltzmann constant times temperature, and then normalized by the partition function, right? But in essence, these probability distributions are in a way similar, right? Like you assign probability distributions to say spin configurations, right? Like in the Ising model or in any of the classical StatMech problems, right? And they're very analogous to the images, to the probability distributions people are interested in machine learning. And so that's what we're going to be looking at. We're going to be using these generative models to study physical systems and so on, right? On the other hand, there's quantum physics, right? Like where we study wave functions, or if you want, the wave function is an object that describes the state of a quantum system, and it encodes all the information you can know about the quantum state that you're trying to study, and it's a function that is very similar to this probability distribution, right? Like this probability of images or probability of spin configurations. And so it's this wave function. See, it's a generalization, if you want, of probability distribution. But ultimately, what's common is that both machine learning and statistical and quantum physics are interested in similarly high dimensional distributions or wave functions, right? And so that's why we want to use, or we want to exploit these tools, this machine learning for physics in a sense. And so that's the reason why this idea works in practice. And apart from that, there's also a lot of commonalities, right? Like the symmetries, high dimensionality, similar structure in correlation functions, both in machine learning data sets, natural images, music, animals moving, pictures of cats, and so on, with respect to the systems that we looked at in statistical mechanics. Okay, so there's a lot of commonalities, right? So here's a landscape of probabilistic models. So this is a bit arbitrary, but it's a like I think a good way to think about it, right? Like so on the y-axis we have algorithmic flexibility, possible queries you can ask about a model, tractability, meaning the number of quantities that you can get out of a model that you train, right? And then on the other hand, we have expressive power, meaning how complicated are the distributions we can model with the model we're interested in, or we're looking at. Okay, and so on the one hand, we have models with high algorithmic flexibility, like mean field theories, naive Bayes, probabilistic tree models, latent tree models, Gaussian mixture models, and so on. So they're, if you want, the more classical statistics type of models. They're very powerful, but they have limited expressive power. However, they allow you, for high tractability or algorithmic queries. You can exploit And so you can, meaning that you can ask a lot of questions about the probability distributions you're interested in, right? Like, for instance, you can compute marginals, which are, if you want, you have probability of x1 and x2 and x3, then it's easy to compute, for instance, probability of x1 or probability of x2 and so on. Okay, so these models are very, very tractable. You can ask lots of questions that are important, but they're not very expressive. And then as you increase the expressive power of the model, then you decrease the tractability. Okay, you start you have a compromise between the two, the expressive power and the flexibility, meaning the number of questions you can ask about this distribution. And so for here, for instance, we have probabilistic circuits, which are pretty interesting and very powerful, but also very tractable. We have matrix product states or tensor trains. They're very powerful again, and like they have a lot of tractability. And then we have this 3 or 4 models. They're called neural autoregressive density estimators, recurrent neural networks, transformers, and they're very expressive, but the tractability is a bit more restricted, right? And then there are the most powerful models that I'm aware of, like variational autoencoders and generative adversarial networks. So they're supposed to be very expressive. They can express very complicated distributions, but they're less tractable. And ultimately, we have, we hope we will have quantum Born machines, which are probabilistic models based on quantum computers. They're supposed to be the most expressive of all of them, but they're very, very, very limited in the type of queries you can ask about them. Basically, you can only sample them, pretty much like a generative adversarial networks, right? And so in this lecture or in this talk, I'm going to discuss a particular set of models. In particular, I'm going to focus on the recurrent neural networks. Okay, and that's going to be the focus of them, because they have this kind of like sweet spot in terms of it has some interesting tractability properties that I'm going to discuss that allow you to do a bunch of interesting calculations and interesting deal with interesting problems in physics, but at the same time, they're very expressive. Okay, so I'm going to focus on those. So they're called autoregressive models. I'm going to explain what this means. And so let's just go ahead with that. What are autoregressive models? So the term autoregressive originates from the literature of time series models, where observations from a previous time step are used to predict the value of the current time step. So it's based on this time series data. It's just the name. So I'm going to introduce these RNNs in the context of modeling probability distributions, because that's the closest in spirit to what we want to do. But they are, they can do a lot more stuff, right? Like not just modeling probability. So just know that I'm going to discuss probability distributions and RNNs, but RNNs are vastly more flexible in terms of like the amount of things you can do with them. But I'm going to discuss just probability distributions and wave functions. Okay, so we can see the probability distribution P of sigma, where sigma is this sigma 1, sigma 2, so n variables. And those variables can go from 0 to all the way through d nu minus 1. Okay, so it's discrete probability distributions with d nu possible values for each of the sigmas. And so there's the chain rule, which I will exploit a lot. So it's that you can express any probability distribution in terms of their conditions. Okay, so this probability distribution can be expressed in terms of probability of sigma 1 times probability of sigma 2 conditioned on sigma 1 times probability of sigma 3 conditioned on sigma 1 and sigma 2, and so on all the way through probability of sigma n conditioned on sigma 1 through sigma n minus 1. Okay, and so the autoregressive part is here, right? Like I here have this arrow here that for you to predict probability of sigma 3, generically, you would need sigma 1 and sigma 2, the previous steps that you saw. And that's how we use this term, autoregressive, right? Like from this literature, because you're using previous observations to predict sigma 3, okay? And so here's one important thing is that if you want to specify P in a tabular form, so this requires exponential resources, right? Like because every conditional has, say, D new values. So you will have the new values to specify this probability distribution. And this is going to be a matrix of this P sigma 2 conditional on sigma 1 is going to be a matrix of D nu by D nu, okay? Because both sigma 1 can take D nu values, and so you have D nu by D nu probabilities, right? And if you go to sigma 3, you have an object that has D nu by D nu squared number of values, and so on, right? Like, so you keep going, you have D nu to the n-1 by D nu. And so that's exponentially big as n grows, okay? So you need exponential resources. But then the insight from the machine learning community is that instead of writing this probability distribution as a tabular, in a tabular form or as a table, you can just parameterize the conditionals, right? Like, so instead of writing them out, you can write models that functions that give you this condition, right? And so that's what alleviates this exponential explosion in the representation of a probability distribution using this this expression, right? And so so that's the idea, right? Like, so we want to handle objects that are very compact and that easy to handle numerically or mathematically. So that's what autoregressive models are, the parameterization of the conditional distributions that appear in the chain rule of probability, all right? And so they have certain advantages, okay? So what are the advantages? So they can be sampled exactly in polynomial time as long as the number of parameters data is a polynomial of the size of the system n, okay? So that's important. And the other thing is key is computing the probability of a configuration. P of sigma is also efficient, again, as long as the number of parameters is a polynomial of the number of of n, the number of spin variables or sigma variables. They can be defined in any spatial dimension, D. So that's important. They're very expressive, but they also simple in that they can contain mean field theories, right? Like, for instance, if you heard of Guth-Wheeler mean field theory, then you can express this mean field theories in terms of a recurrent neural network. We can impose symmetries and other inductive biases, like, for instance, if you're dealing with a system with translational invariance, then we can impose it. We can impose, I don't know, for instance, charge conservation, if you're interested in studying a system with charge conservation. We can impose discrete symmetries. We can do all those things on this type of models. There are some disadvantages. So one is that if you want to compute expectation values with respect to the distribution P that expressed by the RNN or by autoregressive models, then this requires, typically this requires sampling, okay? And for instance, if you want to compute observables in a physical system, if you want to compute gradients, then this typically is done through sampling, which leads to error bars in the estimation. But that's, I mean, it's nothing we can do about it as far as I can tell. And the other thing that is a little bit of a disadvantage is that they're very slow to sample, because you have to sample each of these conditionals sequentially for you to be able to get a sample. So those are the generic autoregressive models. oh, sorry, before going on, so this properties that I just mentioned would remain true if you use this autoregressive models to model quantum states. Okay, so that's important because we will be discussing autoregressive models of the quantum state, and all these properties will remain true. Okay, so what is a canonical example of an autoregressive model is the recurrent neural net, which this is the topic of this lecture. So let me discuss this, right? Like so RNNs, as I said, there's autoregressive models, and RNNs in particular, they parameterize probability distributions through the conditionals. So we will be parameterizing the conditionals, all right? So the elementary building block of an RNN is a so-called recurrent cell, okay? And this recurrent cell, like the main objective of the recurrent cell is to help us specify the conditional, okay? That's what it is. And we do this through a so-called recurrent relation. So what we do is we introduce some so-called hidden state H as a function of, say, we call it time stack or spatial dimension or spatial site and so on. So it's a recurrent relation. So we have this vector H, and it's a nonlinear function of matrix W times this hidden vector at the previous step n-1 concatenated with the input of the RNN, which is sigma. These are the variables that I was mentioning in the probability distribution, plus vector B, okay? And this nonlinear function is applied element-wise on the outcome of this linear, this so-called affine transformation, W times H plus B, okay? So H is a so-called hidden vector. It's, if you want, the object responsible for inducing correlations in the recurrent neural network, and it has some dimensionality, dh, hidden dimension. And this dimensionality, this dh, the dimensionality of this hidden vector controls the expressive power of the model, okay? Meaning that if you make dh large enough, eventually you're gonna be able to describe any probability distribution. Meaning that RNNs, the way I'm presenting them, are universal function approximators. Meaning you can, if you allow DH to grow very fast or very large, then you can express any probability distribution. But that's not what we want. We want to keep the H small because we want compact representation of these distributions. A related quantity is this matrix W is dh plus d nu times dh matrix. It's a real one. And B, vector B is in real dimension dh. There are the parameters of the RNN. Okay, so they control the expressive power through dh, right? So as you make dh bigger, you have more and more parameters, and that's how you make the RNN powerful. F is a nonlinear function, which for the simplest recurrent neural network is a hyperbolic tangent. Okay, so that's the recurrent relation of the RNN, and as I'll show you, it's responsible for inducing correlations between the variable sigma in the RNN. Okay, that's the idea. Okay, and note that if we iterate this recurrent relation, then ultimately Hn was going to be a function of sigma 1, sigma all the way through sigma n-1, right? Like so, if you do this iterative procedure, this is what you end up with for H, right? It's a very nonlinear function of the variables that we're trying to model. The initial hidden state, H0, that you have to initialize somehow. The matrices W and B. And so as this function looks, then it's useful, or it can model conditional distribution because it has the right dependence. Okay. All right. And so we can model this conditional distribution, this conditionals through the use of this recurrent cell. Okay. H0, the initial hidden vector, and sigma 0 are arbitrary. So I typically set them to 0. Okay, so the initial input to the RNN, or they can be trained as well. So you can make them variational parameters. So maybe basically joining or merging them with W and B, so that you can train them and select the best option. Okay, so one thing that is important is that the parameters W and B are shared at each call of the function f, at each call of the recurrent relation. Okay, meaning that this weight matrices and bias vector B are the same at each call. Okay, which is important because then this leads to a very compact representation. Okay, so that's a key part of the architecture of the recurrent neural network. However, this can be relaxed, right? Like, so you can make W n and B n be a function of n, small n, all right? And so this is potentially useful. We use this in some of our examples when we're dealing with, for instance, disordered systems, where you want that each of the variables sigma 1 have their own weight matrices and so on. So this can be relaxed and is potentially useful. I already mentioned this other point is that RNNs are universal function approximator, meaning that they can express any probability distribution. So what are the building blocks? Well, we mentioned the recurrent cell, which I have here. And there's an enrolled version, which is this guy here. I'm going to explain this in detail. And the other aspect that is important for what I'm going to explain is the sampling of the RNN. So let me go ahead with those two. So as I mentioned, so we have the recurrent cell, the recurrent cell, which is this nonlinear function of the input and the W and the hidden vector H that we feed on itself. So that's this green part, the recurrent cell. The input, as I said, it's this variables that we're trying to model. So typically, for what the systems we're going to be looking at, a couple of them, this d nu is going to be 2, meaning that we'll have a binary variable sigma I. So they can take either 0 or 1 or up and down or plus or minus 1. Okay, and we typically represent them through a one-hot encoding, which is basically 0 you map to 1 0, a little vector, and 1 you map to 0 1. So those are called one-hot encodings of this binary variables. Okay, but this generalizes to higher spins, right? Like, or higher local space dimension higher than 2. For instance, if you have 3 here, you would have 0 0 1, 0 1 0, and 1 0 0. Okay, so that's the input encoding. So that it's fed to the RNN cell, which computes this Hn in terms of the input and the hidden states. And then we're interested in modeling conditionals, right? Like, so the probability distribution. So we feed Hn, and we apply a second transformation where we multiply matrix U plus so times H plus some other vector C, such that this looks like a probability distribution S. It's called softmax. And so softmax is just this function e to the vectors that you fed, in this case U times H plus C, and then you normalize. Okay, and so it's a normalized probability distribution, and ultimately that softmax layer represents this conditional distribution that we're interested in modeling, right? And so that's this, and there's U, more variational parameters. In this case, it's d nu times dh, and C is in d nu, are weights and matrices of this so-called softmax layer. Okay, so that's it. That concludes the definition of the recurrent neural network. So input, recurrent cell, softmax layer, which allows us to compute conditional at each time step for a variable sigma n. Okay, so that's it. So there's an unrolled version of the RNN, which is basically this graphical notation that I was explaining can be unrolled over time, right? Like, so you initialize the cell calculation with some arbitrary vector h0, which as I said, I typically set it to 0, and some input variable sigma 0. As I said, I set it to 0 as well, but they can be trained if you want. And then you compute H1, which you pass through a softmax layer to compute P of, so this Y1 is the probability of sigma 1, basically, okay? So let me explain the process. So given a configuration sigma 1 prime through sigma n prime, evaluate P. That's so-called forward pass, okay? So first we compute y1, and then so y1 is going to be a vector with the new entrants, two entries, right? So it's a probability distribution, and then so you have to evaluate for sigma 1 prime, and so you choose the entry corresponding to sigma 1 prime. Okay, so that gives you a number, and you store it somewhere in your computer, and then you bring a sigma 1 prime and you put it here at the inputs of the cell, okay? And you take H1, you compute the softmax, and you get this quantity. You get Y2, which is the probability of all possible values of sigma 2 conditioned on the sigma 1 prime that you're trying to compute, okay? And then, so this is again the new dimensional vector, and then you choose the entry corresponding to sigma 2 prime. All right, and you keep doing this, right? Like you keep doing this until you reach sigma n prime. And so what you've done is you've computed all the conditionals in the, so you've computed this guy, this girl, and so on, okay, until this. So what do you do if you want to compute the probability of the full configuration? Then you multiply all these conditions, okay? And that's how you get this computation as a product of the conditionals you computed above. And this is, as I said, efficient as long as the number of variational parameters, as long as DH is not, it doesn't grow faster. So as long as DH is a polynomial of big N, okay? Why? Because you have some matrix multiplications happening here. Of all of them are going to be polynomials of DH, all right? Because they're matrix multiplications of this type, W times these numbers, which are of the order of DH, and you do this N number of times, right? So it's clearly a linear in Hn, linear in N, and some polynomial of DH. So as long as DH is a polynomial of the number of variables, then this whole procedure is efficient, okay? This is important because it allows us to compute probability amplitudes or estimate probabilities of configurations efficiently. All right. Okay. So let me do one more thing, and then I'll stop 5 minutes or 1 minute for questions. So the other thing that is important for at least for the applications I'm going to be looking at is sampling, right? Like, so we have a distribution, we may want to get samples out of it. All right. And it's very closely related to the process that we just explored. So if you want to sample from a model of a recurrent neural network, what we do is we initialize sigma H0 and sigma 0 to whatever they are, either 0 or train interval variables. We feed them, we compute Y1, meaning that we computed P of us, all possible sigma 1s, right? Like, so it's again a new dimensional vector, and there's a probability distribution, so we can sample this on your favorite, using your favorite computer program. It's just a tiny vector, that you can sample. And so you got sigma 1, say, if it's just a spin 1/2 system, it's up or down. So let's say sigma 1 was up. And then you bring it here to the input of the second call of the RNN. You bring H1, compute H2, and compute sigma, probability of sigma 2 through this vector Y2. So it's, again, a very tiny vector. Let's say probability of up and probability of down if we have a spin 1/2. And then we sample this vector, we get sigma 2, and then repeat the process, okay? And until we get sigma n, and that's how you get a sample out of the RNN. And if you're required, you can also, since you were doing the sampling, you were computing the conditionals, then you can compute the probability of the sample that you just observed, okay, just by multiplying the products. All right, and one key observation about this sampling procedure is that the samples that you get are uncorrelated. Meaning, if you run this procedure once and then you run it twice, there's absolutely no correlation between the sample that you got at the first step and the sample you got at the second one. Okay, meaning that this is a very efficient and provably correct sampling scheme, as opposed to, for instance, what you do when you do Markov chain Monte Carlo, where you have to make sure that you run enough Monte Carlo steps to make sure that your samples are decorrelated, right? Which is important to, like, for estimation of, like, I don't know, expectation values over these distributions and so on. All right. Okay, so here's what we have. So we have a probability distribution represented by the RNN that is properly normalized, because each of the conditionals has been normalized by the softmax layer. So that's important. Its computation is efficient, as I said, as long as the number of parameters remains a polynomial of the size of the system. So meaning dH is a polynomial of the size of the system. And sampling is efficient too. And the samples are perfect. They are uncorrelated and no need to perform Markov chain Monte Carlo simulations, which for some systems can be very expensive. All right. So this is the only autoregressive model that I'm going to explain, but the list of this type of models is very long, and there are more powerful models like transformers, neural autoregressive density estimators, autoregressive flows, masked autoencoder for distribution estimation, pixel RNN, pixel CNN. There's many more. Okay. So let me pause here for a minute and see if there are any questions. Feel free to interrupt in any moment if you like, if you don't have questions right now. But let's pause for a minute.
Hello, hi, are you? Do you hear me?
Yeah, I hear you.
Okay, sorry. So we have this small technical inconvenience. We need to mute you when we ask questions, okay?
That's okay. I can mute myself.
Thanks. Okay. So there was one question during the talk that we found out we have this technical inconvenience. So let's go to this one question and then we go for more.
Sounds good.
Hi. So my question is more a curiosity. Back then, when you talked about the relation between the expressivity and the flexibility of the models, you have a blob in the bottom right where there are basically generative, right here, generative models, right? And I was just curious to know, in your opinion, where you would locate if you have ever heard about normalizing flows, because I would naively expect this to be very expressive and very flexible. So where would you locate them?
Yeah, so I agree that they're very expressive, but they have constraints, right? Like, so normalizing flows, so they have to satisfy some special constraints that these layers are invertible, right? So that imposes constraints on the expressive power. So that's my one comment. They're very tractable as well, but like for instance, like so if you're normalizing flow models probably with sigma 1, sigma 2, all the way to sigma n. So you can compute the amplitude, right? Like the probability you can compute and so on, but you cannot, for instance, compute marginals very easily. Okay, so I would put them somewhere somewhere here. Like, do you see my mouse? Somewhere here. I don't know if you see my mouse, but yeah, somewhere near matrix product states, maybe a little bit toward the left of matrix product states, because matrix product states are more tractable. All right, maybe yeah, so maybe close to the RNNs somehow. So they're like normalizing flows are very close to GANs in spirit, right? Like in that you sample some distribution, some easy to distribution, and then you apply some transformation, and that's how you get your samples, right? But in GANs, this transformation is completely arbitrary. So meaning you can put anything you like, and this is gonna work as a GAN, basically, right? But in the normalizing flows, this transformation has a lot of constraints that it has to be inverted. All right, so that's why they're not as powerful as GANs. All right, yeah, that's my opinion on that. I can't hear.
It's okay. Next question. Or maybe, hold on, we need to go.
Hi, can you hear me?
Hold on.
I hear you, yeah.
Thank you. So I just have a question about the training process. So what loss function you use, and do you need also to train the matrix connect to variable y?
Yeah, so I'm going to discuss the training styles in a minute, but the ones I'm going to be discussing are maximum likelihood estimation. I'm going to discuss what it is. And we're going to be using also like a physical based trainings. Like, for instance, if you have a Hamiltonian and you want this probability distribution to mimic the Boltzmann distribution, then we use like a variation principle based on the free energy, for instance. Or if you're doing quantum many-body ground state search, then you use the variational energy and you minimize it. So, but I'm going to discuss this in a little bit. And yeah, so we train both W, B, and U, the matrix in the softmax layer, as well as the vectors C. Mm-hmm.
It seems that it seems that the autoregressive property of your network induces an asymmetry in that, let's say, evaluating HN requires all spins rather than evaluating H1 only requires the first one. And so how will this influence, let's say, the training if you want to consider spin systems that are symmetric, or if what I said is true, because I'm not sure. But
yeah, it's true. So you can see if I am muted or not. Can you hear me? Okay. Yeah. Okay. Sorry. Yeah. Now I can see. So yeah. So that's true. There's this asymmetry, and it depends on like how you choose your variables, right? Like, so there are natural ways of choosing those variables, but ultimately, if you want to restore the symmetry, then you have to impose it, right? Like, and so in 1D, for instance, this is easy to do if you have this special symmetry. For instance, I don't know. What's this called? Reflection symmetry with respect to, say, the spin in the middle. So what you can do is you can impose that symmetry, and this is like in machine learning, they call this bidirectional RNNs. And so you have to do some work to do it, but it can be a problem. In practice, it's not, but I agree. All right, let me go on if there are there any other questions?
I think that's it. Thanks a lot.
Thank you. Right. So one thing I didn't mention about the RNN, or I mentioned it already, the RNN is they can be. So I mentioned it. Yeah. So they can be defined in any spatial dimension, and so here's how you define it in 2D, for instance, right? So you enrich your RNN cell and you make it a horizontal parameter W and a vertical W, all right? And then so what you do is at each point in the RNN here, ij, right? Let's say lattice site ij or a variable labeled by ij in 2 dimensions. What you do is you take this cell and you make it receive this input states, right? Like so hi j-1 and hi-1 in the computation of your hidden vector hij, right? And so you have a variation parameter for the vertical incoming vector, sorry, for the horizontal incoming vector and for the vertical incoming vectors. All right, and then you take the spin configurations again, the ones that are required, and that's it, right? Like so, the sampling is a little bit well, the sampling and the forward computation go again along a zigzag path, but ultimately you are also encoding the 2-dimensional structure of the lattice if you want when you do this, right? Like, but the sampling and the forward computation that I explained go serially, pretty much in a linear path. So we start here, go here, go here, go here, go here, 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 until you get to the end of the lattice. But at each point in the calculation, you're receiving inputs that respect the locality of the 2-dimensional lattice. So this is very interesting, and it works really well, as I'll show you later. Right. So finally, I want to discuss recurrent neural network wave functions, right? Like, so how to go from this classical picture of the recurrent neural network into how to generalize them and make them represent wave functions, which we'll discuss right now. So these were introduced by my PhD student Mohammed in this paper. So there are two wave functions that we're going to specify. So the wave function A and wave function B. So wave function A is basically there's no change to the architecture. All right, so we just really don't do any change to the architecture. So it's just the RNN that I explained earlier. The outcome is again probability conditional distributions, P1 through Pn. The sampling operates in exactly the same way, and the wave function part is just the interpretation, right? So there's a family of made by Hamiltonians, or a family of quantum states written in some computational basis, say sigma z or sigma x. I don't know. You can choose any complete basis function and represent that wave function in that basis. And so what's so special about this family I'm trying to discuss right now is that their amplitude in that computational basis, sigma x or sigma z, is always positive. All right. So this is a very special family of wave functions for which the specification of the wave function is equivalent to specifying a probability distribution. All right. So then basically what you have is a coherent superposition of the square root of a probability distribution, right? So that's the defining characteristic of this family of quantum states. But in general, wave functions are complex value, right? So this is not going to represent all possible quantum states that we can think of in terms of this wave function that I'm considering. However, there's a very important family of quantum states that we're interested in. In particular, they're ground states of so-called stochastic Hamiltonians, right? And so stochastic Hamiltonians are Hamiltonians in which the off-diagonal elements of the Hamiltonian are always negative, all right? And there's a theorem that it's due to Perron and Frobenius. It's called the Perron-Frobenius theorem that guarantees that the lowest energy or lowest value eigenstates of matrix, whose all like the off-diagonal elements are negative, it implies that the ground state or the eigenstate with the lowest eigenvalue is positive or negative. All right, and so for those family of Hamiltonians, the ground state satisfies this condition that the amplitudes of the wave function has the same sign. All right, and so for those type of problems, then this wave function A, this coherent superposition of square root of a probability distribution, is powerful and it's sufficient to describe those or some of those ground states. Okay, and so that's why we have this seemingly simple wave function here. But then, of course, we want a more general set of wave functions that encode a phase or a sign structure in the wave function in whatever computational basis you're using, right? Like so, and so what we do is we take the square root of p, but then we multiply that by a phase factor. All right. And what we do to define this phase factor is the following. So we have the softmax layer here, S. So that's untouched with respect to the RNN, the traditional RNN. But then we add another layer that outcomes a local phase. And we do that through a so-called soft sign. So instead of a soft max for a probability, we have a soft phase or soft sign. And that outputs a phase at each time, at each call of the RNN cell, all right? And so we get this phi1, phi2, phi3, all the way through phi n. And what we do is we compute the phase of the wave function as e to the I phi sigma, where phi sigma is the sum over all these phases that we collected as we unroll the RNN. All right, so it's very simple, and if you want, the computation remains efficient, the wave function remains normalized as if it was just a probability distribution, and the sampling that I was mentioning remains the same, because when we sample, we typically sample according to the amplitude square of the wave function, which means that this phase factor will disappear in the sampling procedure. And so all these properties that I was discussing, the tractability of the computation of the amplitude of the wave function, as well as the sampling, they all remain efficient, again, as long as the number of parameters doesn't grow fast. All right, so that's the definition of the RNN. Finally, and this is related to a question I got earlier, how do we train these models? So, and we're going to explore two different training styles. And then
hi, Juan.
hello.
Okay, perfect. So we had this problem with a loop. That's when someone was speaking from here, we had like infinite loop going, and now it's working. Do you want us to interrupt you with questions, because now we can, or you prefer?
Yeah.
Okay, good.
Interruption is good.
Good. So now it's gonna be probably more interactive. Sorry for that.
No worries.
I think that we have like 30 seconds, and yeah, and I think we are ready.
All right, so we can get started again. So as I was discussing earlier, we explained what an RNN was, how to compute the probability of a configuration, and I explained how to sample the RNN efficiently. But I didn't tell you how we train these models. So I'm going to explore two different ways of doing it. One that is based on data. So I call that a data-driven approach. Within the data-driven approach, there's a bunch of ways of training these models. I'm going to explain just one of them, and one that is very popular and it works really well for some systems. It's called maximum likelihood estimation. So it's based on a very important principle in statistics. So this definition is from Wikipedia, it's very good. So in statistics, maximum likelihood estimation is a method of estimating the parameters of a probability distribution. So the parameters in our model are the parameters of the RNN data, I call them, but they encompass the matrix W, the bias vector B, the matrix U, and the vector C of the softmax layer. And if you want sigma 0, the initialization of the RNN inputs, and H0, the initialization of the hidden vector. And so the maximum likelihood principle maximizes a likelihood function so that the model under the observed data, or that the model that we're using assigns high probability to the observed data. Okay, so that's the principle. And it makes sense because so we have some observations that we assume that come from a probability distribution P. And so it means that if we're observing them, then they must have had high probability under this unknown distribution P, all right? P of X or P of sigma, all right? So that makes sense, right? Because if we observe events, they're probably likely to occur. Like they probably assign high probability under this some model that we're looking at, all right? So our distribution, as I said, is P theta given by the recurrent neural network with parameters theta. And the loss function or the objective function is the likelihood, so the probability of the data under the model that we're using, P theta. And this is to be maximized because these observations are assumed to be likely, okay? That's the spirit of the maximum likelihood estimation, a very important principle in statistics and also in physics. So a bit more details. So given a data set of observations sigma I, so where I labels the different experiments that we run, there's observations ID, identically distributed observations, and independent identically distributed observations. So meaning that these experiments are independent of each other. That's an important assumption here. And we have NS of these experiments, or NS of this data point sigma I. Okay. So that's the so-called data set, right? That comes out of our experiments or our thousands of pictures on the internet and so on. And then we have a likelihood function, right? So what is the likelihood function? Well, we're gonna assume that this data is IID, meaning that they're independent, and we're gonna assume that this that the probability of this observation under the model is just the product of the probability assigned to each observations. And this is because these observations are independent. So if we go and see again the chain rule, we have this probability of the different variables, And then if there's no dependency, then this conditional disappears, and all you get is a product of observations, right? That's what we're using here. And so what we have is a likelihood function, or the likelihood assigned, like that the model assigns to this data set is basically the product of the probabilities assigned to each observation, right? And the maximum likelihood principle tells us that we should maximize this object, right? With respect to what? With respect to the parameters in the model, right? Because we want the model to assign high probability to what we observe, okay? And so that's expressed in here. So the parameters that we should consider optimal for the model is maximization of the likelihood function with respect to parameters data. All right. So in practice, so this is the principle, but in practice, we basically take the log of the likelihood and then change its sign. So this is called negative log likelihood, and then we minimize it. All right. So basically, we would minimize this negative log likelihood. And to do that, well, there are many ways, right? Depending on the distribution that we're dealing with. So one way is we basically take the derivatives of this likelihood function, and then we set them to 0 and find if we can solve analytically for the optimal maximum likelihood estimation parameters. So this is rarely the case unless you're dealing with a very simple distribution. Like for instance, if this p theta is a Gaussian distribution, then you can solve the problem analytically, and you can find theta of the maximum likelihood, say for a Gaussian distribution or for a Bernoulli distribution. In those cases, you can always do it analytically, and it's a very instructive exercise to do. However, in practice, for the RNN and so on, we would have to use gradient descent techniques, iterative techniques to do this minimization, right? And this gradient descent techniques, I'm hoping you've already seen this in earlier talks by Eliška. So we basically, what we do is we take the gradient of the negative log likelihood, which we can compute with respect to the parameters in the model, and then we update the parameters using this rule, right? Like, so where gamma is a small number, it's called the learning rate. All right, and then we follow this because we're going against the negative, like the gradient, which is always, you can prove this, always gives you, for a small enough gamma, always gives you a lower value of the negative log likelihood. Eventually you converge, and the parameters that you find are either a global minimum, a global maximum or a minimum, or a local one. But what the hope here is that you end up on a decent solution of this optimization problem. So can I ask if you've seen this technique already in the first 2 lectures, maybe?
Yes, we've seen that before.
Awesome. Okay, great. Yeah, so we will follow the same strategy. So here I want to mention we will have to do back propagation through the recurrent neural network. And if I have time at the end, I will discuss it a little bit. But it's very similar in spirit to the back propagation you may have seen for the neural networks in the first 2 lectures. Okay, so it's not very different, but I'll discuss it maybe later if there is time. So that's the spirit, right? Like of the maximum likelihood estimation. I want to mention this is not the only principle we can approach that we can use. So there are other techniques which can help you train these models. So one of them is so-called adversarial training, which is also powerful, and we can train the RNNs using this adversarial training. And the idea is that you have the data set, and then you have the RNN, and the data set, it's there, and then you ask the RNN to produce data, right? Like through sampling. And then you have another neural net which is trained to recognize whether this data that you feed into it comes from the real distribution or from the RNN. All right. And then you train both this discriminator, so-called discriminator, and this generator, which is the RNN in this case. And then this is framed as a game. And the idea of the game is that the RNN should fool the neural net that distinguishes real data versus generated data. And so you train those two, the RNN and this discriminative neural network until this data is produced so perfectly that the RNN is basically producing data that is indistinguishable from the data set. So that's a popular training style for this models. There's also moment matching, which is basically you train the model to reproduce the moments of the distribution. There's variational inference, maximum mean discrepancy, all sorts of techniques that can use data to train these models, and they all have different advantages and so on. But I'm not gonna, yeah, go ahead.
May I ask you just a question? Isn't the method that you just talked about also kind of a variational inference? Because you're trying to infer the parameters of a variational approximation of your distribution, right? So it should fall under the same category or not?
Yeah, so that's, yeah, so I agree with what you said. It's a variational technique, but variational inference have a little bit of a different meaning in that you don't exactly compute the log likelihood, which in this case, it's possible. In some models you can't. So what people do is they create a variational bound on the log likelihood, right? Like, so that's the meaning of this variational inference that I have here. It's a way of training where you can't access the log likelihood, but you have a bound on it. All right. So I agree with what you said. What we're doing is a variational optimization of the log likelihood. We can compute it exactly for this model, but there are other models that you can't. Okay, and so you compute a bound on it that is computable, and that's why they call it variational inference. Do you agree?
Didn't have the microphone. Yes, thanks a lot for the explanation. It's clear.
Yeah, like for instance, variational autoencoders, they cannot be trained on the log likelihood. So you use the so-called elbow variation bound on the likelihood. And then the other style of training is based on quote unquote physical laws or Hamiltonian-driven approach. So this is very popular in our community, but it's also gaining a lot of momentum in the ML, in the core machine learning community, especially for solving differential equations. Okay, so in our case, this differential equation is one particular one that is very interesting but very difficult, is the Schrodinger equation, right? So this is the other technique or the other approach that we use. It's Hamiltonian-driven or Schrodinger-driven. You call it whatever you like, but it is basically using a physical principle to train the models. So these models, I mean, people, you always say you need a lot of data to train them, but ultimately you don't need, all you need is a gradient signal, right? Like you need a learning signal, right? And so that signal can come from data, which is this approach, but also from an equation, right? So you don't need data, you need just an equation that tells you what, that tells you how to guide your model or how to optimize it, right? And so in classical statistical mechanics, there are variational principles that we can use. So for instance, we can train, if you're interested in equilibrium properties of a StatMech problem, then you have a model P theta, and so you can try to make it mimic the Boltzmann distribution of a system described by some Hamiltonian H, an Ising model, for instance, or the Potts model, or whatever you want, or the Sherrington-Kirkpatrick model, or a glassy system that is very difficult to sample, and so on. So, and for this, we can, is there a question?
I don't see it.
Okay.
No, sorry.
No, I heard something, but maybe it was just myself. So anyway, so you can use variation principles to do this. And so
Maciek has one. Sorry.
Okay.
So can you comment shortly, what is the status at this moment of applying this kind of things to really do spin glass problems, both short range and long range?
Yeah, so it's there are some examples. So they're here. So one of them, the earliest I know, is by Dian Wu, Lei Wang, and Pan Zhang, and they attack the problem of solving statistical mechanics using this variational autoregressive networks, and it works really well. They can compute partition functions and estimate free energies with this approach. So that's in this PRL, and we have this paper. We call it variational neural annealing, where we tackled solving constraint optimization problems on spin glasses. So basically finding the ground state of spin glasses, both the simple ones like the Edwards-Anderson model, as well as the Sherrington-Kirkpatrick, so fully connected spin glasses, and it works really well. So I'll show you one example later on about how this compares to quantum Monte Carlo and simulated annealing, if that's okay.
Yes, thanks.
Right.
Thanks.
Thank you. So let me go ahead, and so we can use a variational principle, and it's this equation here. So we can compute, or we can associate a free energy to our model P theta as the expectation value of the energy, or the Hamiltonian, minus T, temperature times its entropy. Okay, and this is going to be always larger or equal than the real free energy corresponding to the Boltzmann distribution. All right, and so what we can do is we can minimize F theta, this quantity here, until we reach a quantity that is very close to the real free energy, right? So F is the true free energy of the system at temperature T, basically the free energy of the Boltzmann distribution. And the entropy of the distribution S of P theta is this object here. It's the entropy of our model. And so we can train the model using this principle. And so how do we do it? Well, the free energy F theta can be estimated from samples. So that's why I was discussing sampling with so much in so much detail, right? Like, so where free energy is basically an average over samples of so-called local free energy, where F log is the energy of the Hamiltonian that we have, plus T times the log of P. Okay, and remember, I insisted a lot that we needed or that we wanted to compute the probability of some configuration sigma, and it's because of this, right? Like, because if you want to compute this free energy, we need to be able to compute the log of P, which is possible because of the fact that we have a normalized model, or because of the fact that the RNN is normalized, properly normalized. Okay, so that allows, so I made a comment here, but I already explained. So this requires access to samples according to this distribution, hopefully good samples. In this case, they're exact samples, so they're the best you can get, and access to P without expensive calculations of the partition function. So we don't have a partition function because the model is normalized by construction. So that's why we find this approach of this RNN or this autoregressive model so powerful for this type of learning style. And likewise, the gradients of the free energy can be computed, and they're fast to compute, and so on. They're given by this expression here. So it's again in terms of samples and quantities that we can easily access. So the samples and the log of P. Again, we have to do backpropagation to compute these derivatives, and I'll try to explain the backpropagation later on if I have time. And then what we do is we simply follow the gradient updates, the gradient descent update that I was explaining earlier, and that hopefully you've already seen in Eliška's talks. So note that, as I said, we had this data style learning, but in here there's no data. All right, so the data is gone, right? We have a physical principle. However, if you like this idea of explaining things in terms of data, then you can think of this samples that you collected out of the model as your training data. That's if you want, but I don't think there's any need for like bringing data into this game. Okay, so this is all based on physical principles like optimization of the free energy. So there's no data involved. We can move on to quantum systems. Okay, so we can extend this idea of variational training of the model based on a physical principle and use it to tackle ground states or even dynamics of quantum many-body systems. All right, and so what we do is we promote the recurrent neural network into a quantum state. So we go from a probability distribution into a wave function psi theta of sigma in some computational basis. And of course, I explain this whole recurrent neural network wave functions because we were going to explain that idea. So what I mean by wave functions is this either this reinterpretation of the RNN or this complex valued RNN wave function. All right, and so how do we do it? Well, as I said, we promote the RNN to a wave function, and we modify the objective function E, and we, instead of having this free energy, we compute the variational or the energy or the expectation value of the Hamiltonian. In this case, it's going to be a quantum Hamiltonian on the wave function that we're interested in optimizing. This quantity, I forgot to write it, is always greater or equal than the true ground state of the system. Okay, and so if we minimize E theta, then if this optimization goes really, really well and the model is expressive enough, then this function eventually is going to approximate the ground state of the system, and this quantity is going to approximate the ground state of the system. Okay, both E theta and its gradients are available again through sampling of the RNN. All right, so let me explore this a little bit. So both E theta and its gradients are available through sampling. So here's the expression for the energy, right? So here we have the energy. We introduce two resolutions of the identity. So one here and one here in terms of complete basis, sigma. And then we can rewrite this whole thing as two sums, right? Like sum over sigma of the amplitude square of the wave function in that computational basis, and a second sum over sigma prime, which is this object. It contains the Hamiltonian or the matrix elements of the Hamiltonian, sigma and sigma prime, and the ratio of the wave function at sigma prime divided by the wave function at sigma, right? And so note that in principle, these two sums are exponentially big. So we need to do something about them. We cannot compute them exactly. So the first sum, look, so this is psi squared. This corresponds to a probability distribution. We call it P theta. This is again the real part of the RNN that we can exactly sample. And so we can approximate this sum over sigma using importance sampling, so Monte Carlo average. And so we basically take this expression and we basically approximate it with samples from the RNN. So sigma is drawn from the amplitude square of the wave function, basically from the P of the RNN. So let me remind you that, so if we square the amplitude of this wave function, so this phase goes away and all we get is samples or the average over the probability distribution P sigma expressed by the RNN. All right, so that's this part here, this sampling according to the RNN, and then the local energy, which is this expression here. Again, so we have to evaluate it. And the sum, in principle, it's over an exponentially large Hilbert space, right? So, but the Hamiltonians we're typically interested in are very sparse. So there's an assumption here that we should be able to compute this local energy, this given some configuration sigma seen by the RNN or by the samples from the RNN, we should be able to compute the matrix elements H sigma prime that are connected to sigma efficiently. So that's an assumption, right? That the Hamiltonian should be local, or that given some configuration sigma, there should be only a polynomial number of sigma prime non-zero elements in H. All right, and then so we assume that we can compute this efficiently, this local energy, which is true for many Hamiltonians of interest. So that's it for the energy. The gradients can also be computed again through sampling. So the energy gradients, the exact expression is given by this sum. So it's given by the amplitude square of the wave function times the gradient of the wave function with respect to some parameter theta j, one of the parameters in the wave function, divided by the wave function itself times the local energy. All right, so then again, this can be approximated, right? Like because it contains this wave function squared, that is the probability. So we can use sampling again. So we go ahead and do the sampling, and this is the expression you get. It involves the local energy, the derivatives of the wave function. So again, we need to do this backpropagation through the recurrent neural network to get this expression. But in principle, this is easy to compute. And then we just basically follow the direction of the gradient descent update, which we have here. So where we replace the energy, so the free energy by the energy here. All right. So that's it for the, let's say, quote unquote, theory of the discussion. So what I'm going to do next is to show you a couple of examples that we've worked out this last couple of years. Okay. So if there are questions, I'm happy to answer them now or proceed with the examples.
Yes, there's a question. Hold on.
Thank you. So how would you go about computing higher eigenvalues like excited states? And by how would you go, I mean, in terms of optimization and in terms of changing your RNN architecture? Thanks.
Yeah, so I have never done this before, but I know what people do in variational Monte Carlo, and even in machine learning, people do this type of things. So what you do is so first of all, you start with the ground state, all right? You optimize it, and then you take a new RNN, a complex one, and then you modify the cost function, right? So what you do is you compute the energy subject to an orthogonality constraint. So basically, you are minimizing the energy plus a Lagrange multiplier on the, for instance, on the overlap between the ground state that you just optimized and this current wave function. All right. And so this is such that you penalize quantum states that are non-orthogonal or parallel, right? And so then you do that and you get hopefully the first excited state. All right. Yeah. I said hopefully because this is not guaranteed to converge. Then if you want to go to the next excited state, then you do the same. But now you have two more constraints: orthogonality with respect to the ground state and the first excited state. And you minimize the energy with those constraints. Luckily for the RNN, computing these overlaps is very easy, which is not true in all wave functions, but this is doable here. Okay. I don't know if that answered the question more or less. You keep doing this until you hit however many eigenstates you want.
yes, that answers. Thank you.
I also have one question. So normally when people do this for restricted Boltzmann machine for the training, they do this stochastic reconfiguration. Are you also doing that for this recurrent neural network?
So we didn't do it, but it's possible to do it. That's right. So it's a better optimizer, absolutely. But we have not done it for the systems we have looked at.
Okay.
Any other questions? If not, feel free to ask me later, whenever you want.
Yes, I think I don't see more questions. Thanks a lot.
Awesome, thank you. So first is learning a quantum state with RNNs. So this is, if you want, a data-driven approach. So let me explain this. But first, let me tell you how we represent the quantum state, which is a little bit also interesting. So typically, a quantum state is traditionally described as a density matrix. And it tells you everything about, we can possibly know about the quantum state. This density matrix has everything. It's a quantum state is a positive semi-definite Hermitian operator, trace one, acting on the state space. And this family of states forms a convex set. For one qubit, it's just a block sphere, the familiar block sphere. So it's this here. A quantum state is just a vector in this block sphere. But there are alternative ways of representing the quantum state, and one of them is based on probability distributions. And you can see where I'm going, right? Like we, instead of how to say it, so instead of changing machine learning so that it looks like quantum mechanics, we're changing quantum mechanics so that it looks like machine learning in a sense. So we're going to be representing the quantum state in terms of just probability distributions. So how to do that? We'll use positive operator valued measurements. And they're basically how you represent measurements that you apply on a quantum state, okay? They're positive semi-definite operators, and the sum of them adds up to 1. And then there's a fundamental relation in quantum theory that links quantum theory with the experiment. Because when you go and do an experiment on a quantum state, all you get is outcomes of measurements, okay? And this relation is called Born rule. And it relates the quantum theory, meaning the density matrix, the measurement operators that describe your experiment, and the probability of observing the outcome A, which is PA. And there's a family of POVMs called informationally complete. They are such that this probability distributions of the measurement outcomes contains all the information about the quantum state. Okay, so and we're going to be using those. And that what this means is that the relation between rho and P can be inverted. So here we go from rho to P. But if you have a measurement that is informationally complete, then you can back up the density matrix from the measurement outcomes, okay? And so that relation is what we're going to be using, okay? So here is the relation. So I'm skipping a lot of details, but there's a relation between rho and this probability distribution, so long as this information, so long as this measurement is, probes a lot of information about the quantum state. And so our model for the density matrix is this object here, where P is replaced by the RNN, by the recurrent neural network. All right. So this is what we do. The insight that we have, we parameterize the statistics of the measurements, and then we invert this relation. And this P is going to be the RNN, right? So this is the autoregressive model. Why? Because it allows for exact sampling, as I was saying, and allows for tractable density, meaning that we can compute this P of the measurement. And we're going to be using maximum likelihood estimation, which is the statistical inference technique that I introduced to model this P out of measurements on a quantum state. All right. So it's very simple, right? Like it's really, you go ahead, and you prepare an unknown quantum state. You apply a measurement that probes enough information about the quantum state, and you repeat this on and on. And so, meaning you collect a lot of statistics such that you can then try to reconstruct this quantum state. All right. And so this is collecting the data set that we use to train the model with a maximum likelihood estimation. And ultimately, we infer a reconstruction of the quantum state consistent with the measurement outcomes. And so basically, this is our raw. We have a language model, a recurrent neural network model here, and our density matrix is this. So as simple as that. And so that's what we did. We didn't do an experiment. We just numerically simulated a measurement quantum state in the lab using some prototypical quantum states. And so to do that, we use DMRG, and we produce ground states of some typical Hamiltonians, like the Transhill-Ising model on 50 spins, and the Heisenberg model on the triangular lattice. All right, and then so these are the correlation functions of the DMRG state in red or orange, and we collected a lot of data, and these are the reconstructions of the state given by the RNN. All right, so it's green, which, I mean, they look very, very decent, I would say. These are expectation value of sigma x on the different sites, and this is two-body correlation function sigma 1z, sigma 1 iz as a function of I, and we see again good agreement. And here's the spin-spin correlation function for the ground state of the Heisenberg model in 2D for an 8x8 lattice. And again, we see this is the correlation functions of the synthetic state, and this is the correlation function of the recurrent neural network. That's the first example. So we have successful reconstruction of quantum states from data. Now an example on the recurrent neural network wave functions. So this is ground state search. All right.
Okay, sorry, there is a question. Yes, I need to find it. Yeah.
Correct.
And two questions. I start.
Hi, I have two questions. So the first one is, you don't have to know what the form of the Hamiltonian is here, right? In order to do this kind of state tomography.
No, you don't have to learn the form of the Hamiltonian. You don't even need a Hamiltonian. It's just that we just took examples that are
examples. Right. Okay. Well, actually, we have two more questions. So one is, what is your limit in the system sizes? Can you scale to large system sizes, or it becomes harder and harder? And the third question: why are RNNs the sort of most suitable architecture for this kind of problem? I mean, could you do it equally well with some other type of neural networks, or why RNNs?
Yeah. So first, so what was the first question again? Sorry, I forgot.
The size, yeah. Can you?
Size, yeah. So we went up to hundreds of qubits, around 200, I think, if I remember correctly. I think in the paper it's up to 100 spins, but we reached up to about 150, 200, and it becomes expensive, but still doable. All right. So yeah, we can go up to hundreds of spins. And the other question was about the architectures, right? So RNN, it's just in practice really good, but you can use other architectures. However, note that there are two advantages here. So one is the exact sampling and the tractable likelihood. So for instance, we tried using the RBM, the restricted Boltzmann machine, which is very popular, and it couldn't handle learning more than 5 spins very accurately. Okay, whereas the RNN, we were able to go really big. We don't know quite We're not quite sure why that was the case, but we just couldn't make it work as well as the RNN. But you can try other models for sure. I just don't know about the scalability of these other models. All right.
Okay, thanks.
Thank you.
Yeah, I just saw in the title of the slide, learning ground state of local Hamiltonians. And so is it a sum on nearest neighbors only in your Hamiltonians?
Yes, so these are Hamiltonians where this sum over ij are restricted to nearest neighbor, nearest neighbors. Yeah, and the same here. So
did you try more complex Hamiltonians and so more entangled quantum states?
Not for the reconstruction. Although in a different study, we tried typical states, which are very entangled, and it works, but the size of the system is very limited for those states.
Okay, yeah. So I guess my last question is, what's the limit of your approach? Because as you said, you did 100 spins. And so what's the limit? So
there are multiple limits, right? Like, so one of them is the amount of information encoded in a quantum state. So if you have a typical state, then typically every amplitude of the wave function matters. Okay, and so that makes the whole thing, the whole learning very difficult, because you have to learn an exponential amount of information as you make the size of the system bigger. And so you have to make the RNN as expressive, which means that your RNN should be very, very powerful. Basically, you don't gain anything by using the RNN. So that's the big limitation, right? Like that as the complexity of the quantum state grows, then your approach suffers. The other is that these RNNs, as I mentioned, they're relatively slow to sample. So if the system gets too big, then the sampling suffers. I would say those two are the main limitations.
Thank you. Are there more questions? I don't think so, so you can continue.
All right, let's go ahead. So this is recurrent neural network wave functions. So here we do the opposite. We tweak machine learning so that it looks like a quantum system. And so we studied these recurrent neural networks as approximations of ground states of many-body Hamiltonians. So this is for the transitional Ising model with 1,000 spins. So this is the, as we train the model to approximate the ground state, this is the relative error with respect to a DMRG calculation, and it's very small, and as well as the energy variance, which again should go to 0 if we hit the true ground state. So this is energy relative error in the energy for the J1, J2 model in 1D for different values of J2. And again, we see energies that are very good. These are comparisons between the transitional Ising model in 1D with the MRG, so correlation functions ZZ and XX. And we see the agreement between the MRG and the RNN is pretty good. This is in 1D where the MRG is really unbeatable. This is entanglement entropy. And everything is consistent with the MRG. Of course, the MRG is more accurate, but that's 1D where the MRG is really the best that we can do. But then we went to 2D, we used this two-dimensional RNN, and we tried to tackle the ground state of the transitional Ising model, and these are the results. So this is the ground state, sorry, the variational energy. And when you compare with the one-dimensional RNN with the MRG, which is not so suitable for 2D, and different ansatz called pixel CNN, and what we found is that the 2D RNN for this transitional Ising model is always better than the rest of the techniques by a little bit. and so we were pretty happy. This is this 2D powerful RNN. It seems to work really well. So for ground state search. Then finally, I wanted to tell you a little bit about.
We have a question.
Hi. I'm a bit confused. Can you go 2 slides back to the RNN states? So is this in some way equivalent or very much related to IDMRG, or am I missing something? Like these RNN states these RNN networks that you have per site, is this different RNN networks, or is it the same network that is processed in time when you sample?
So this is sort of finite lattice, so we didn't do infinite systems, and this DMRG is not IDMRG. This is finite size DMRG, and the RNN is just the same. But I agreed. I mean, the RNN cell is always the same, so in principle, this could be used to try an infinite type of calculation. We just don't. I mean, we have a missing ingredient, and I can discuss this offline if you want. But yeah, there's some possibility to do infinite system sizes with the RNN as well.
Okay, thanks. Just a question about the RNN wave functions. Why do you separate the phase and amplitude? And is that better than just taking complex parameters?
We don't know how to do complex parameters because we lose the sampling ability of the wave function if we do it that way. We don't know how to do it with complex parameters, and there are different ways of parameterizing the phase in principle, because the only thing is, I mean, we could separate completely the phase and decouple it from the probability part, but this has some interesting characteristics, and they're the following: that in the mean field limit, this wave function reproduces some simple known sign structures like the Marshall sign and so on, which happen, for instance, for the ground state of the transializing model, for the Heisenberg model, and bipartite lattices. And so we kept it like that. Basically, it's the simplest thing we could think of that works and that reproduces some known sign structures that are out there in some important Hamiltonians. But there's flexibility in how you choose this, and we don't know, we didn't explore it fully.
Just why can't you sample the wave function?
Because you break up the you break up the. I mean, if you have a phase that is not, let's see. I mean, if you. The problem is if, like, it depends on how you do it. I mean, there's ways you can separate so make the whole thing complex and still sample, but there are ways in which you can ruin the autoregressive structure of the model.
Okay, thanks.
But I can be more detailed on offline. I can comment on this score. Okay, I'll think a little bit more about it. The last thing I wanted to tell you, but I only have 5 minutes, is perhaps combinatorial optimization. Let me just flash you a couple of slides, and because it's related to a question I got about spin glasses, right? So, and the idea is that in combinatorial optimization, the idea is to solve the ground state of an easy classical Hamiltonian, okay? And so we wanted to see if the fact that these recurrent neural networks can be exactly sampled would bring an advantage for sampling spin glasses or ground state of spin glasses, right? And there are many problems that can be framed in this, within this like optimization or combinatorial optimization, like the traveling salesman problem, nurse scheduling, vehicle running problem, and so on. So there's a technique called simulated annealing, which does that using basically Metropolis algorithm to sample the Boltzmann distribution. So we asked the question, can we use the RNN instead, which doesn't use Markov chain Monte Carlo, but that is only variational approximation of the Boltzmann distribution. All right, so that's the question, and so basically that's the idea, right? So instead of so in simulated annealing, we have a sampling of the exact Boltzmann distribution using Markov chains, right? Which can be very slow and they're inexact, basically because these distributions are very difficult to sample if you have a spin glass. And so we do that, and we do variational simulated annealing. That's the idea, where the model is wrong. It's only a variational approximation of the Boltzmann distribution, but we have exact samples, right? So swapping the wrong sampling of the exact distribution with the exact sampling of the wrong distribution. Does this produce anything useful? And so we try to simulate simulated annealing using variational free energy and recurring. That's the question, and so we do that using the RNN, and let me show you the results, because that's the only thing I'm going to have time to tell you. So we tried the Edwards-Anderson glass, which is a two-dimensional square lattice spin glass, and these are the results. So I'm going to focus on B. Okay. So this is simulated annealing as a function of how many annealing steps I take. And this is the residual energy with respect to the true ground state of the system. So this is simulated annealing. It's a technique based on Monte Carlo, and this is simulated quantum annealing, a technique based on quantum Monte Carlo. And what we found is that if you give the RNN enough time, it beats both the traditional simulated annealing and simulated quantum annealing by several orders of magnitude. So meaning that we can get better sampling of the ground state space of the Edwards-Anderson model. All right, and this is on a 40 by 40 lattice, so this is relatively large. And so we were pretty happy. And then we tried to look at fully connected spin glasses like the Sherrington-Kirkpatrick model, and the so-called Wisher-planted ensemble, which is very difficult to solve. And what we found is that at long annealing times, the RNN beats both simulated annealing, simulated quantum annealing in all the spin classes that we looked at. And so that was just a comment related to a question I got earlier. And let me conclude, right? Like, so we introduced these RNNs and showed examples of applications in quantum many-body physics and combinatorial optimization. So we did quantum state reconstruction and ground states of 1D and 2D systems. But there's more, so we've done a lot, and there's multiple applications of the RNN and multiple new projects that we could come up with. Like, for instance, we did simulations of quantum circuits based on the autoregressive models. We did neural error mitigation in near-term quantum simulations. We've done simulations of open quantum systems and transfer learning. We've done a lot, and I hope you're excited as I am about this type of autoregressive models and this type of problems. And yeah, with that, I would like to thank you all for the attention and the organizers for the invitation. Thank you.
So are there more questions?
Thanks a lot. That was indeed very interesting. So one more question. What are the challenges to do a real-time evolution, or like the unitary evolution with the Hamiltonian with using RNNs? Can that be done, or what are the difficulties?
Yeah, so this can be done. I think the difficulty is, so as far as I understand, the problem is not in the expressive power of the model, but in the approximate integration of the equations of motion that you find for the parameters of the RNN. Okay, like and in general for those neural networks. And so that's the issue. The issue is that when you integrate these equations of motion, so theta dot, you have a quantity, some matrix, is a big matrix, it's called S matrix. It's very similar to stochastic reconfiguration, Fubini study metric, or the Fisher information metric. And so this quantity is computed through sampling, okay? And so when you compute it through sampling, this matrix comes with an error bar. It's a noisy matrix that you get out of this equations of motion. But the problem is not the computation of the matrix. That's probably okay. The problem is computing its inverse, because this matrix is ill-defined. It turns out it results in an ill-defined matrix. And so you have to do some regularization on this matrix. And regularizing this matrix is tricky, but people came up with techniques in a recent paper by Markus Schmidt and Markus Heil. So they have, I think, the state of the art in the integration of these equations of motion. And so the same is going to be true for the RNN, right? Like, so I think they explored RNN, but didn't work as well. They ended up doing convolutional neural nets. And this has, I believe, one of the state-of-the-art results in dynamics of many-body systems. But the issue, again, is the integration of the equation of motion of the parameters and the noise induced by the Monte Carlo calculation of this Fisher information matrix. I don't know if that answered the question.
Thanks.
Fantastic, I would say, very nice. But I have the following question. So if I remember well, in the case of Sherrington-Kirkpatrick, actually there exists even rigorous proof that the Parisi picture of replica symmetry breaking and multiple, let's say, components, thermodynamic components in the spin class space is rigorous, correct? In the case of short-range Edwards-Anderson, there is a famous Hughes-Fisher picture of the kind of droplets, as they call it, or droplet model. And this is not rigorously proven. And of course, if you ask Parisi, he will tell you that his picture is always valid. And other people are saying that it is not. Can this approach help something to resolve this controversy? And the similar question actually is, well, it's not similar, it's a proposal. You should apply this method to Hopfield model with the long-range interaction. It will be a total fun to have neural networks solving neural networks.
That's right. Yeah, so for the first question, I don't know the answer to that. Like, we have not tried to resolve this this question. And we know there are methods to solve this. Like, for instance, the Edwards-Anderson model can be solved in polynomial time by dynamic programming and so on. So these are two, if you want, Sherrington-Kirkpatrick and Edwards-Anderson, kind of like warm-up exercises for us. We didn't know much about them, and we still don't know. So we still don't know how powerful this is to really resolve these issues, but it would be fun to try. Yeah. So, and then for the Hopfield, yeah, that would be super fun to try. And the other last comment I had was the final model we tried, where we think this proved to be useful, is this Wisher planted ensemble that I didn't have time to describe, but we still produce really accurate results, better than the traditional techniques. And yeah.
Thank you. So are there more questions? If not, let's thank Juan again. And
thank you so much, everybody, and enjoy the rest of the school.
thank you.